Hello students, in this video we will study about electric potential. What is electric potential and how to derive the expression for electric potential due to a point isolated charge. Okay, the concept of electric potential, what it is, you see, this is electric potential. Okay, to define this, first let us consider a point charge plus Q situated at O in space. If it is situated at this point, it will create electric field because a stationary charge will act as a source of electric field. Around this, it will create electric field. What is the electric field that it creates at a distance r? This electric field is given by 1 by 4 pi epsilon naught Q by r square. This is the electric field it is going to create at a distance r. So theoretically, if r becomes infinity, then electric field becomes 0. This we know. It means practically this distance will not be infinity, but at certain distance electric field is going to become 0. That means, let us suppose that influence of electric field exists up to this region. That means where the influence of electric field will end, where there is no influence of electric field, I can treat that point as infinity. Let us consider this at distance as infinity. At this distance or at this point where electric field is going to end, I will place a test positive charge. A unit positive charge is placed at that point. Since this is positive charge, what is the direction of electric field? Electric field will be away from this charge. Electric field will be directed away from the positive charge. Okay. If this positive charge, test charge, comes just within this region, it will experience a force of repulsion. Okay. What is the force of repulsion that is experienced by this test charge is, that is F is equal to Q naught into E, and this force will act along the line joining the two charges away from charge like this. Suppose, let us consider, I want to bring this test positive charge from infinity to any point inside the field. From infinity to any point inside the field. That means I am going against electric field. When I am going against electric field, to move this charge, I have to do some work. A fixed amount of work should be done because I am going against electric field. See, in physics, if you are going against any force, you need to do some fixed amount of work. Suppose, for example, if I want to bring this, if I am bringing this marker from here to here, if I drop it, it will fall down like this. If I want to lift it from this point to this point, I have to do some work. That means I am going against gravity. When you are going against any force, you have to do some work. So, to move this charge from here to here or any point inside the field, we have to do a fixed amount of work done. That work done per unit charge. Suppose, for example, to bring this charge from here to here, I am doing 100 joules of work. How many joules of work I am doing? 100 joules. For Q naught charge, I am doing 100 joules work. For 1 unit charge, how much work is done? That means this is the amount of work done. For Q naught charge, W is work done, 100 joule is work done. For 1 coulomb, what is the work done? W divided by Q naught. The amount of work done per unit positive charge in moving the charge from infinite distance to any point inside the field. How much work I am going to do? That work done divided by that charge, or work done per unit positive charge, it is called as electric potential at that point. Is it clear? if I want to define electric potential at this point, that means it is the amount of work done in bringing 1 coulomb of charge from infinity to this point. How much work is done? That is divided by charge will give electric potential at this point. If I want to bring it from here to here, amount of work done will be different because I am going still closer to the charge facing electrostatic repulsion. That means how this quantity is defined is the amount of work done in moving a unit positive charge, test charge it can be considered, from infinity to a point inside the field, from infinity to any point inside the field against the direction of field. It is very important that against the direction of field is called electric potential at that point. Is clear? How much work I am doing, that divided by the charge brought, that will give me the potential. Potential is usually denoted by capital letter O. That means the potential at any point is equal to the amount of work done per unit positive charge. Amount of work done per charge, per unit charge. That means I will divide this. This is the formula of electric potential from its definition. Follow this? Okay. Now let us try to derive the equation for electric potential at a particular point. This is the definition. Make a note of definition. We will derive the expression for the field. Okay, noted down. This is the definition. Amount of work done per unit positive charge. Why I need to do the work? Because I am going in against electric field. That means I should do some work. Whatever is the amount of work done divided by that charge will give electric potential at that point. That means it will be different for different points. Okay, then see how to derive the expression. Let us say I want to derive the expression for electric potential due to this charge at this point, which is situated at a distance r. Okay, which is situated at a distance r. Then what I will do? Let plus q is a charge situated at point O. Situated at point O in the space. Okay. Let P is a point. Let P is a point at which electric potential is to be determined or is to be calculated. Okay, let P is a point at a distance r, at which we want to find the electric field. Means such that, let's suppose OP is equal to R. Okay, at this point I have to do the work. I have to find the potential, not work. Then what is the potential by definition? At this point, what is potential? the amount of work done in bringing this charge from infinity to this point. That work done divided by this charge will give me the potential at this point. By definition, the amount of work done in bringing this charge from infinity to this point and dividing that work by Q naught will give me the electric potential at this point. First let me find the amount of work done, then we will divide it by Q naught to get the potential. To calculate the work done, to find the work done in moving this charge from infinity to point P, this is very large distance. If I consider theoretically, this is very large distance. Then for that purpose what I will do, I will not calculate the amount of work done in bringing this charge from infinity to this point. I will select a point at the finite distance within the field. Let A is a point at some finite distance from charge Q. Then I will calculate the amount of work done in bringing this charge Q naught from A to certain point, another point, through a small distance. Then I will get a small work done in moving. Suppose the distance of this A from this point is x. What is x? X is a finite distance. A is a point which is at some finite distance x from the charge. Let me consider another charge, another point B here, which is a part of x, which is a small displacement dx. Let us consider. This is a part of x, which is dx. Then what I will do, instead of calculating the amount of work done from infinity to R, infinity to point P, I will calculate the small amount of work done in moving the charge from A to B first. Then I will integrate this work to get the total amount of work done within the limits of infinity to R. See, when I bring this Q naught from infinity to P, see, originally this is Q naught, this is plus Q1. Q naught is here. At how much distance it is there? Distance between Q naught initially is infinity. I am bringing this Q naught from infinity to point P. That means distance is R. That means I am reducing this distance from infinity to R. I am reducing this distance from infinity to R. So what are my initial distance, what are my distance limits? I should start from infinity and I should reduce this distance to R. First let me reduce this distance by dx, a small amount of work done in bringing the charge from A to B, I will calculate. Then I will integrate this amount of work done for this distance limits to get the total amount of work done. Then for this purpose what I will do, see here, let A is a point at a finite distance x from Q. Okay. Then what is, can you tell me what is electric field at A? Electric field at A is given by, what is the distance of A from this Q? X. Then E will be equal to 1 by 4 pi epsilon naught Q divided by x square, which is acting along OA like this. Acting along OA. Then what we'll do, we'll try to find this. This is the electric field. Here an electric field exists, which is E, which is given by 1 by 4 pi epsilon naught Q by x square. Then this electric field will, suppose if I am bringing this positive charge at this point, then this positive charge placed at E will experience at this much force. Placed at A will experience this much force in this direction. That means the charge plus Q placed at this point is experiencing a repulsion force which is equal to Q naught into E, where E is given by this much. So in which direction it is experiencing the force? Along OA, like this. I wanted to move this Q naught through a small displacement dx from A to B. If this is experiencing a Q naught E force this side, then what should be my applied force in the opposite direction? I have to apply a force of minus Q naught into in this direction, so that I can move it from A to B through a small distance dx, displacement dx. Why I am calculating that small amount of work done? Because I want to calculate the work done within the infinity and r distance limits. I will move it for a finite displacement dx. I will get a small amount of work done. Then I will integrate that small amount of work done in between these limits to get the total amount of work done. Then for this purpose, what I am doing, you say, what is my force applied? See, this I have to apply a force. I am doing work against which force? I am doing a work against Q naught into E. This is the force acting. I want to move Q naught from in this direction. Then this is dx. This is F. This is dx. Then this is F in this direction. I want to move it in this direction through a small displacement dx. Now can you tell me what is the angle between force and displacement? Is 180. Then the small amount of work done, in moving the charge Q naught, the charge plus Q naught from A to B, through a small displacement, dx is, what is the work done formula we know? What is the formula of work done? dW is equal to F dx cos theta. This will be F dx cos theta. See, this is force acting, this is the displacement. And what is theta? Theta is 180. Since theta is 180, then dW will be equal to, cos 180 is minus 1. Then it will be minus F dx, or I'll write F dx, one step, F dx cos 180. Then this implies dW is equal to minus F dx. This is the small amount of work done. We know what is the value of F now. F is Q naught into E. Let us substitute Q naught into E, and in place of E we will write this, and we will try to find the small amount of work done. Okay, make a note of this. We will continue. Noted? Can I repeat? Okay. Let me calculate dW first, and we'll integrate this. You remember the definition of electric potential. By definition is the amount of work done divided by Q naught. Then what is my dW now? This dW will be equal to minus of F. What is F? Q naught into E into dx. Then this dW will be equal to minus Q naught. What is electric field at this point? What is electric field at this point? Electric field is 1 by 4 pi epsilon naught Q divided by x square into dx. This is my small amount of work done in bringing the charge from A to B. But I don't want to bring it from A to B. I should move it from infinity to point P. That means I should reduce the distance from infinity to R. Okay? Then the total work done, see, the total work done in moving the charge from infinity to point P, I should reduce the distance, infinite distance, to R. See, what is the work done? And try to calculate. Infinity to point P will be W is equal to, this is integration of dW, all the parts of, from here to here 1 dW will be there, from here to here 1 dW, from here to here another dW. That means through the small displacement dx, 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 dx like this, we have small amount of work done dW, dW, dW in between this range. Then that distance will be from infinity to R. Then what is this work done? From this will be infinity to R. I will write this work done here. Will be 1 by 4 pi epsilon naught. I will take this Q naught this side minus outside. Okay. Then this will be Q naught into capital Q divided by x square into dx. Leave x and dx in the integral sign. Take remaining all those constants. Take remaining constants outside. Then this will be W is equal to, I will take all the constants outside. This will be Q naught into Q divided by 4 pi epsilon naught x. Epsilon naught. Then this will be the integration of infinity to R 1 by x square dx. Understood? In the integral form, integral sign, integral symbol, it should have only x and dx. With respect to x we are integrating. This will be minus q into q naught divided by 4 pi epsilon naught. What is integration of 1 by x square? Use this formula. Integration of 1 by x square is nothing but x raised to minus 2 into dx. See, 1 by x square it is dx. This will be x raised to minus 2 into dx. Then what will be this? X raised to n dx. This is x raised to minus 2 plus 1 divided by minus 2 plus 1. This will be x raised to minus 1 divided by, this is minus 1. If I bring this x to the denominator, it will be 1 by x with minus sign. The integration of 1 by x square is minus 1 by x with the limits infinity to r. This minus, let me make it plus, or else you can substitute these values here. See, this will be minus q into q naught divided by 4 pi epsilon naught. You know how to substitute the limits of integration. Wherever x is there, first you put r. Wherever x is there, upper limit. This will be minus 1 by r. Then it will be minus. Wherever x is there, you put infinity. Then it will be minus of minus plus. It will be 1 by infinity. 1 by infinity is going to become 0. Then I will leave it. Then w will be equal to, this is minus into minus, it will be plus. Then it is 1 by 4 pi epsilon naught q into q naught divided by r. This is not potential. This is the total amount of work done in bringing this positive charge from infinity to R. Then I want potential. So by the definition of electric potential, I have V is equal to W by Q naught. Then electric potential at point P. Electric potential at point P. At point P is V is equal to W by Q naught. This I am divided by Q naught. Q naught get cancelled. Then potential will be 1 by 4 pi epsilon naught Q by R. Okay. This is the electric potential at a distance R. Note it down. Okay, noted. Now observe these two formulas. Two formulae what we studied for electric potential, electric field also. See, this is a point charge plus Q. At a distance R, a point P is there. This is a distance R. What now? At this point, if I ask you what is electric field, then your answer must be 1 by 4 pi epsilon naught Q by R square. Q by R square. And it's the same point if I ask you what is electric potential, then your answer must be 1 by 4 pi epsilon naught Q by R. See, what is the difference between the electric field at a distance R and what is electric field at a distance, electric potential at a distance R. Electric field at a distance R is inversely proportional to R square, but the electric potential at a distance R is inversely proportional to R due to a point charge. This is the formula of electric field and this is the formula of electric potential. Okay. Now we will study one more term. What is electric potential difference? Electric potential difference. If I ask you what is the difference, what is the electric potential and what is electric potential difference, and you see inside the field, if I ask this is plus QR, this is point O, situated at point O, then the amount of work done in bringing the charge from infinity to point P. At infinity, we take potential as 0. At infinity, we take potential as 0. There will be no influence of the field. At this point, potential is V. Then what is the potential difference? It is just V. But if I take the point, 2 points inside the field, if I take a point here, if I take another point here, B, if VA is the potential at point B and VB is the potential at point B, the amount of work done in bringing the charge from infinity to A is VA and the amount of work done in bringing this charge from this to this is VB. Then what is the distance? What is the electric potential difference between these 2 points? Potential difference, suppose that from infinity I have brought a charge from infinity to A, I have done 100 joules of work done. From infinity to B I have done 140 joules of work done. Then what is the difference in the potential? It will be 40 per unit charge. Per unit charge it will be 40 joules. That means in bringing the charge from infinity to A, I have done 100 joules of work. In bringing the charge from infinity to B, I have done 140 joules of work. Then if I ask you what is the amount of work done in bringing the charge from A to B, it is 40 joules. That means the potential difference between the 2 points is defined as the amount of work done in bringing a charge from one point to another point, where both have potentials. This have potential 100, this have potential 140 per unit charge. That means what is the amount of work done in bringing the charge from A to B? From A to B, amount of work done is 40 joules, which is nothing but the difference in the potential of 2 points. So what is potential difference? Potential difference between 2 points. Potential difference between 2 points inside the electric field. Between 2 points in an electric field. In an electric field is defined as, is defined as the amount of work done, in moving a unit positive charge, from one point to another point against the direction of electric field. This is very important. Against the direction of electric field. Here in this case, we need not to do any work to move the charge from B to A, because if a positive charge, if you keep it, naturally it will move from higher potential to lower potential. But when I want to bring the charge from A to B, I need to do the work. How much amount of work I have done, that gives me the potential difference between A and B. See, the potential difference between A and B. This is at higher potential, this is at lower potential. Then I will write this as VBA is equal to the amount of work done in moving the charge from A to B divided by charge Q naught. That means, which is VB minus VA is equal to work done in bringing the charge from A to B divided by Q naught. Then you can calculate the amount of work done. Amount of work done is Q naught into VB minus VA. What is VB minus VA? It is the potential difference between A and B. Then this is W is equal to, work done can be defined like this. The charge which we are moving from A to B, this is Q naught. This is charge which is moved from A to B, whatever it may be, plus 1 microcoulomb, plus 2 microcoulomb, plus 9 microcoulomb, whatever the charge which we are moving multiplied by potential difference between A and B. Only this much. What is PD stands for? Potential difference. Here we will get an important conclusion from this equation. What is charge? What is work done? The charge which we are moving from one point to other point, that charge should be multiplied by potential difference. This is electric work done. This whatever work done we studied in mechanics, this work will be equal to force into distance. It is mechanical work done in moving a body from one point to other point. This is the electric work done. Work done against electric field. This we call this work is equal to charge which we are moving from one point to other point multiplied by potential difference. That means it is very clear here, work done depends on what? Work done depends on potential difference between these 2 points. See, if I bring the charge from A to B, this is A, this is B, lower potential, higher potential. If I bring it from A to B, then charge into potential difference gives. If I bring it like this, then also work is equal to charge into potential difference. If I bring it like this, then also work is equal to charge into potential. The charge which we are moving multiplied by potential difference. That means work done depends only on the potential difference. That is, work done depends only on potential difference. That means from which point to which point we are moving. Only on potential difference means only on initial and final position. Initial and final positions. The work done depends only on the initial and final positions, but not on path followed. It is very important. But not on the path followed. Work done does not depend on the path followed. It depends only on the initial and final position. What is the potential difference between these 2 points? It depends only on potential difference. It does not depend on the path followed. We are doing the work against electrostatic force. If work done, we studied in first year, if work done does not depend on the path followed, work done against any force or in the direction of any force, by any force. If work done against any force by any force, if it does not depend on the path followed, if it depends on only initial and final position, then that type of forces are called as conservative forces. They are called as conservative forces. This indicates me that electrostatic force is always a conservative force. Okay? Make a note of this point. It will be helpful to us. The work done against electrostatic force depends only on the potential difference between these 2 points. That means depends on only on initial and final position, but not on path followed. If work done is not depending on path followed, such forces are called as conservative forces. Okay? Make a note of these points. So this is the potential difference and electric potential. Now let us see electric potential due to system of charges. Clearly, to say electric potential is not a vector. Electric potential is a scalar. This point you should note. Electric potential is a scalar. Electric potential is a scalar quantity. Okay, it will not have any directions. So in the calculations, in solving the problems related to electric potential, we need not to worry about direction. But in case of electric field, which is a vector, we have seen the directions of electric field, then we calculated the net field. Here, in case of the problems related to electric potential, we need not to worry about the direction because it is a scalar quantity. And while calculating the electric potential, you see, remember this point, if it is plus q at a distance r, see, this is plus q charge and I want to find the potential at a distance r, then what I will write? What is my formula? 1 by 4 pi epsilon naught, I will write q by r. If it is plus, I will write plus. If it is negative charge at a distance r, if I ask you what is potential at this point, then 1 by 4 pi epsilon naught, I will take minus q by r only. But while calculating the electric field, we used to take the magnitudes of charges. But while calculating the electric potential, just at a distance r, it is q by r. If this charge is plus, keep it plus here. If charge is minus, then minus q by r. It is one thing. Then electric potential, what is the formula? Electric potential formula is Q, W by Q naught, work done per unit charge. Then what will be its units? Its units will be work by charge. Work by charge means the units will be joule per coulomb, or I can write this as J bar C, joule per coulomb. Yeah. Then, or it is also called as volt, the symbol V. If I do 1 joule of work done in moving 1 coulomb of charge against electric field, then it can be taken as 1 volt. Follow this. 1 second you remember these things. If it is plus, you take it as plus. If this charge is minus at a distance r, then you will take minus q by r. No need to take the magnitude of charge, because it is a scalar quantity. We are not worrying about the directions. We are taking the charge values as it is they have given. Plus, plus. If it is minus, minus. In the formula also you write minus. Understood? Now we will go for electric potential due to system of charges. What is the SI unit? Remember, SI unit of electric potential is volt. Electric potential due to system of two charges. One important thing what we are discussing here is how to find the neutral point, as we have calculated it in case of electric field. Same calculation we are doing here also. For a system of two charges, we will calculate the electric potential. You can calculate it any point. First, we will try to understand what is the neutral point, how it should be calculated for a system of two charges. Like electric field, if in case of electric field, what we studied, if there is a system of two charges, the electric field null point, neutral point will exist between the charges. If it is a system of unlike charges, the neutral point will exist outside the charges. But in both the cases, neutral point will be closer to the charge of smaller magnitude that we studied. Remember it. If it is plus Q1, if it is minus Q. If I say this charge, if it is plus Q1, if it is plus Q2, charges, they are like charges of different magnitudes. These are unlike charges of different magnitudes. On the line joining these two charges, there will be some point at which electric field will be zero. For like charges, suppose if I say magnitude of Q2 is more than magnitude of Q1 in both the cases, then the electric potential, electric field I am talking about, what we studied in the electric field video. If this Q2 is more than Q1, if these two charges are like, then null point exists between the charges and it will be closer to the charge of smaller magnitude. Which charge is small in magnitude? Q1 is small in magnitude. Therefore, neutral point exists closer to the Q1. In case of unlike charges also, neutral point exists on the line joining the two charges, but it exists outside. Still it is closer to the charge of smaller magnitude. What we studied it for electric field. For electric field, when you want to find the neutral point, this will be a point where net electric field will be zero. And for a system of charge, the neutral point for electric field is a unique point. There will be only one point where net electric field can be 0. No other point will be there. But in case of potential, it is slightly different. See, remember, this is for electric field. For electric field, what is neutral point? Neutral point means it is a point at which resultant field is 0. If it is a system of like charges, neutral point exists between the charges. If it is a system of unlike charges, neutral point exists outside. But in both the cases, neutral point exists closer to the charge of smaller magnitude. If Q1 is small, then it will be close to Q1. It will be close to Q1, far away from Q2. This is for electric field. When you want to calculate the same for electric potential, then you see. If I take first one, it is a system of two like charges of different magnitudes. Here if I take Q1, this is Q1, another charge will be there plus Q2. Let us suppose these charges are of different magnitudes. If these charges are of different magnitudes, wherever you see on the line joining the two charges, the potential due to this charge will be plus whatever may be the distance. Potential due to this, if charge is positive, potential is positive. If charge is negative, potential is negative. Since both these charges are positive and potential due to both these charges at a particular point, at any point you take, whether it is inside or outside the charges, that means at this point also potentials will be added. At this point also potentials are positive, both are positive, they are added. At this point also potentials will be added. That means for a system of two like charges of different magnitudes, the point of zero potential does not exist at any finite distance. It may be zero at infinite distance. Okay? If it is a system of unlike like charges of different magnitudes, see at this point also both the potentials are positive, they will be added. At this point also both the potentials are positive, they will be added. At this point also both the potentials are positive, they will be added. No direction. You should not put any directions because I told you electric potential is a scalar quantity. So all these points, at all these points, electric potential will be, total electric potential will be positive. V1 plus V2, V1 plus V2, V1 plus V2. There exists some potential at all the points. The potential of at the point of zero potential is not possible at anywhere at finite distance around this system. Therefore, a point of zero potential does not exist at any finite distance. If it is a system of two unlike charges, a system of two unlike charges of different magnitudes, then what happens, listen it. Then let us see, this is one charge plus Q1, this is another charge minus Q2. On the line joining the two charges, where neutral point exists, neutral point means total potential at a point should be zero. Let me suppose magnitude of Q2 is more than magnitude of Q1. Whatever may be the signs, they are different. So magnitude of Q2 is more than Q1, or Q1 is less than Q2. Then where the neutral point exists? Neutral point exists outside also. See, at this point potential due to this charge will be plus and potential due to this charge will be minus. That means a neutral point exists outside. Why I am taking this side? Why not this side? Because Q1 is less side. If Q1 is less, let us say this is plus Q1, this is plus Q2. If I say that neutral point exists here, if I say that neutral point exists, let us suppose, in between I will take, in between let us suppose that neutral point exists here. Potential due to this charge will be plus and potential due to this charge will be minus. If I take this point outside also, same situation will be. Potential due to this charge will be plus, potential due to this charge will be minus. Okay, if I say that this neutral point is at x1 distance from Q1 and it is at x2 distance from Q2. The following is, it is at x1 distance from Q1 and x2 distance from Q2. At this point, the potential of this will be plus and potential of this will be minus. Then what is the total potential at neutral point? Vn is equal to V1 plus V2. This potential must be 0, I am telling. This at neutral point means it is potential 0. That means V1 must be V1 plus V2 must be equal to 0. At n, V1 plus V2 must be equal to 0. What is V1? It is 1 by 4 pi epsilon naught Q1 divided by x1. Follow this, Q1 by x1 plus 1 by 4 pi epsilon naught minus Q2. E plus I am writing here. Here if I put minus Q2, this will be negative. Then this will be x2. Then this total potential will be 0. Then if I take this 1 by 4 pi epsilon naught common and put it to right side, then what I will get is Q1 by x1 is equal to Q2 by x2 I will get. What it shows is, see, Q1 by x1 is equal to Q2 by x2 means what? Which Q by x is constant. Q by x is constant means Q is directly proportional to x. Q is directly proportional to x means, see, Q1 by x1 is equal to Q2 by x2. I told that Q2 is more. See, this Q1 by x1 is equal to Q2 by x2. It shows that Q by x quantity remains constant. Charge by ratio will be same. Charge by distance ratio will be same. Which means Q is directly proportional to x. If this magnitude of the charge is more, then distance should be more. Which indicates me that if Q2 is more than Q1, if Q2 is more, then x2 should be more or less. Q is directly proportional to x, I am telling. If Q2 is more than Q1, which implies that x2 should be more than x1. x2 is more than x1. That means this neutral point is far away from Q2 and close to Q1. This distance is less and this distance is more. See, whatever, whether you are calculating it outside or in between the charges, you should always take neutral point closer to the charge in smaller magnitude. One example we will see this. Depending on this, one example we will solve, we will understand this. It is a textbook problem. How many neutral points exist? Two neutral points. One will be outside the charge, one will be inside. And in both the cases, that neutral point exists. Neutral point means what I mean. What neutral point refers to? The neutral point is a point at which electric potential is 0. Okay, and it exists in two positions, one in between the charges and one outside the charges, only for the system of unlike charges, not similar charges. Okay, let us consider this problem will be 2 point charges, 2 point charges, 5 into 10 raised to minus 8 coulombs and minus 3 into 10 raised to minus 8 coulombs are 16 centimeter apart. 16 centimeter apart. Find the position or positions on the line joining two charges where electric potential is 0. We have to find the positions of those points at which electric potential is 0. Note the question. Note the question. I will solve it for both the positions. Noted? Okay. There exist two charges. You can find this is, what is this? 5 into 10 raised to minus 8. It exists at this point. This is minus 3 into 10 raised to minus 8. Exists at this point. What is the distance between these 2 points is 16 centimeter. I told you, if it exists in between the charges, neutral point exists in between the charges, it will exist closer to this charge because it is smaller in magnitude. It is small in magnitude. Neutral point exists towards small charge. Let us say neutral point is here, in between the charges. Same case if I consider outside the charges. So this is, what is this? 5 into 10 raised to minus 8. This will be minus 3 into 10 raised to minus 8. Then this distance is going to be 16 centimeter. If it exists outside, where it can exist? It can exist outside the charges, either this side or this side. I told you it should be closer to the charge of small magnitude. Which is small in magnitude? This is small in magnitude. Therefore, neutral point exists outside like this. Now if I want to find that point, let us suppose the distance of this point from this 5 into 10 raised to minus 2, it is x. What is the distance between these two? This is neutral point. This distance will be 16 minus x. Then if it exists outside, the distance between these two charges, you can write this, you can clearly observe. This is the point, this is null point. Let us suppose that distance between this, whatever you make it, this side also x, this side also. Let us take distance between neutral point and this is x. So what is the distance between neutral point and this 5 into 10 raised to minus 8 coulombs is 16 minus x. Let us suppose neutral point is at x distance from this charge. Then what should be the neutral point distance from larger charge? Will be 16 plus x. In two cases I will solve this problem. Let neutral point exist. Let neutral point is at distance x. You should mention this with respect to which charge you are taking x. at a distance x from which charge? From -3 into 10 raised to -8 coulombs I am taking. You can take it at a distance x from this charge also, but whatever you take, you should mention it in the question. Then at this point, case 1, the neutral point existing in between the charges. In between the charges. Very simple problem. See, at this point two potentials will be there. Then that should be equal to 0. V1 plus V2 must be 0. What is V1 you can say? Potential due to this point. Potential due to this charge I can say. V2 is potential due to this charge. Whatever it be. Then this will be 1 by 4 pi epsilon naught. I will write just K. Then this is 5 into 10 raised to -8. K stands for what? 1 by, I will write it, 1 by 4 pi epsilon naught. This will be 5 into 10 raised to -8 divided by, what is the distance? 16 minus x. Then this is negative charge, it will be minus. Then it is 1 by 4 pi epsilon naught. Then I write minus, I have taken this side. This will be 3 into 10 raised to -8 divided by x. This will be equal to 0. Total potential. This is V1, this is V2. Net potential is 0. Then if I put this negative sign or this quantity that side, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught get cancelled. 10 raised to -8, 10 raised to -8 also get cancelled. This will be 5 by 16 minus x is equal to 3 by x, which implies that 5x is equal to, this will be 3x, no, so 3 into 40, this will be 16, 48 minus 3x. Follow this? It will be 8x is equal to 48, which implies that x is equal to 48 by 8 will be 6 centimeter. From this charge it is at 6 centimeter and from this charge it is 10 centimeter. To which charge it is close? To the charge of smaller magnitude. And for this outside case also you can calculate this. See, this type of problems will be asked in board exams. Outside, case 2 I will take. Outside the charges. These simplifications you can do it. Outside the charges if I take, so this is x, this is 16 plus x. Following same steps, you can write 5 divided by 16 plus x is equal to 3 divided by x. Same, 1 by 4 pi epsilon naught, write all the formula and cancel. Then which will be equal to, this is 5x is equal to 16 into 3, it will be 48 plus 3x, which implies that it will be 2x is equal to 48, which implies x is equal to 24 centimeter. That means x is equal to 24 centimeter. From this charge it is at 24 centimeter. From this charge it will be at 40 centimeter. 16 plus 24. That means it is away from the charge of larger magnitude and it is close to the charge of smaller magnitude. See, this is all about electric potential and how to find the neutral point of electric potential for a system of charge. One point will exist in between the charges and one neutral point exists outside the charges. In both the cases, neutral point exists closer to the charge of smaller magnitude. That you have to remember. If you find both the positions, then problem will be completed. Okay? Let us discuss the electric potential due to system of 3 charges, 4 charges like that in the next video. Okay, thank you.